Capillarity is such a common phenomenon. In fact, we are breathing, and inside our lungs, exceptional capillary phenomena is taking place. Our wounds heal because, in part, driven by capillarity. Capillarity affects the mixing of oil and vinegar in our salads, and also the migration of L-naples and D-naples in water, the storage of CO2, the long-term persistence of methane and oil in reservoirs trapped by a silt layer, and it affects every soil near the surface where it is above water, so when the water table is below the surface. So if it is so important, we have to dedicate a few videos, a few recordings to understand the phenomena that give rise to capillarity. And the first one is something that is quite unique. You may have seen mosquitoes or spiders that actually sit on water, and where the legs pose, you see how the water bends, where the legs are actually exerting the weight of the insect on the water. And that gives us the idea that this almost like a thin latex membrane at that interface. And that is what we are going to call interfacial tension. And for the purpose of these lectures, we're going to use the term gamma to refer to interfacial tension. Now, it is important to recognize that this is not a spring being pulled, because when we have a spring that we are pulling, the force increases with the displacement. This is not the case. If I were to pull a film of water, actually I would see that the force required remains quite constant. So a better mind model to think about is, imagine that we have lots of spherical magnetic particles, and actually you can purchase them and test the concept that I'm trying to describe. A large number of them, create a layer, and now begin peeling off this one, and as you peel them off, you will begin popping one after the other away from the surface. That is the interfacial tension that we are talking about. In other words, if I would have a syringe and I inject water to create a water droplet, the interfacial tension that is holding that water droplet together is the same as if I continue injecting and the water droplet increases. It just happens that more molecules go to the interface, but it's their attraction that is holding that interfacial tension constant. This is an important concept to understand. And so interfacial tension emerges at all interfaces. It reflects how much one substance likes the other. So it's really a concept of, are we matching each other? What is the attraction between our surfaces, our molecules? So the interfacial tension is, like here, we are pulling, and how much we displace as we pull, so it's going to be in units of millinewtons. That means 10 to the minus 3 newtons per meter along, if this was a long body into the board. And so many times this is referred as millinewtons per meter, but please don't get confused. This m is not this m. This is millinewtons per meter. So these are the units of interfacial tension. Now, if it is all about different fluids and substances liking or disliking each other, now we can make some important predictions. For example, let's consider the first, and that is, if I have water and this is air, I'm going to measure an interfacial tension water-air equals to 72 millinewtons per meter. Please realize how small this quantity is. Now, if I run this experiment in a different way, and this air will actually be a mixture of CO2 and nitrogen and oxygen, let's say that I just put oxygen or methane and any gas that I control. This is once again water. And I begin pressurizing this other gas. Let's say that this is CO2, carbon with 2 oxygens, non-polar molecule. And at the beginning, where the density of the gas is very low, there is high mismatch between the two. So this one will remain 72 millinewtons per meter. But if I continue increasing the pressure of the CO2, and now I have a large number of molecules, there will be more compensation between the unbalanced forces in the water. This is the water here. And because there is more compensation, there is less mismatch. So this interfacial tension here will decrease to probably 30 to 40 millinewtons per meter. So there is a significant decrease when we increase the pressure of the gas outside. The mismatch is also pronounced with other liquids. For example, oil and water is in the order of 30 millinewtons per meter. So both of them are liquid. There are lots of molecules. So it's not a matter of density. It's a matter of mismatch between the molecules that leads rise to that interfacial tension, that degree of unhappiness at the interface. We're going to see that this is going to get more interesting when we put nanoparticles or surfactants. But let's hold on to the concept of interfacial tension here, and let's look at the other component of the response of fluids, immiscible fluids at interfaces. Please let me know that CO2 does dissolve in water and it leads to carbonic acid, so there is some solubility, but it saturates, and at that point it doesn't dissolve anymore. So at that point is when we talk about immiscible fluids, even though we realize that there is some degree of miscibility early on until the dissolution and diffusion takes place. When we see a droplet on a surface, sometimes we recognize that the droplet is sitting quite straight. It doesn't want to wet the surface. This is a substrate. Could be a mineral or any other substrate. However, sometimes the water really likes the surface and wants to spread on the surface. So we're going to measure this angle as the contact angle, and we're going to call it theta, and here is theta as well. And in this case, we say that the liquid is non-wetting with respect to the surface. However, in this case, the liquid likes to wet the surface. So this new parameter that we are referring to is called the contact angle. Now, what does the contact angle depend on? Well, we go back to the 1820s, and that is the work by Young, and that will become Young's equation. And so he did the following analysis. He said, let's look at the surface, and this is, let's call this water, and we're going to call this air, and this is a solid. The interfacial tension between air and water is trying to contract the particle, water, air, interfacial tension, air, water. However, there is a liking of air to the substrate, and so this is the interfacial tension, air, solid. And likewise, there is an interfacial tension between the water and the solid. And the rest of his analysis follows then. If this is the contact angle theta, then let's look at the force equilibrium. On the one hand, gamma air water times cosine theta. We are doing summation of forces onto the horizontal plane. Gamma air water cosine theta has to be equal to gamma air substrate minus gamma water substrate. Therefore, the cosine of theta is equal to gamma air solid minus gamma water solid divided gamma air water. And so once again, the interfacial tensions is a measure of how much one substance likes the other, and that will determine the cosine angle. Now, when we run, so this is Young's equation. When we actually put a water droplet on a plane and we begin tilting the plane, sometimes we see something as follows. This is the droplet, and it doesn't show the same contact angle as it recedes with respect to the contact angle as it advances. So this is theta recede, and this is theta advance. So it appears that there is a hysteresis. This is the substrate. There is a hysteresis in the contact angle. And there are different ways to look at this. It's actually boundary of knowledge these days. But let's go back to Young's equation. You see, the fact that the interfacial tension air-water is pulling means that there must be a resistance at the base. So there is, let's assume that that resistance is adhesive. We could do the same analysis if it is frictional. And so we recognize that there is an adhesion force here, that when we are pushing, the adhesion force is resisting, but if we were advancing or receding, the adhesion force would pull back. And so now we can write the cosine theta is going to be equal the same equation as above, gamma air solid minus gamma water solid divided gamma air water, but we need to take into consideration the adhesion force. And that gives me different phi advancing, different than phi receding. So it gets tricky as to in what direction the invading fluid is progressing. But now we have all the ingredients to begin computing some capillary forces and capillary effects in porous media. So far, we have recognized the importance of interfacial tension and contact angle, and they are continuously present, and there is an interplay between them across the porous medium. So now let's see some implications. For example, the first one is capillary rise. Consider a capillary tube and a water bath. So if the capillary tube is glass and is very clean, it tends to be water wet. In other words, the meniscus tends to form like that, and all this becomes water. And this is what we're going to call the capillary rise, HC. So let's compute the capillary rise, given clearly this is at equilibrium. If we wait long enough, the capillary rise will be at equilibrium, and so there has to be the sum of the forces in Z has to be equal to 0. And so what are the forces? Well, the weight of the capillary body of water, so it will be HC times the area, which is pi r squared, times the unit weight of water. And now please be cautious, because we're using gamma in this case for unit weight to avoid confusions between interfacial tensions and unit weight of water. Let me just say that this is G raw water, realizing that that is the unit weight of water indeed. And so that is the force that is pushing down. This is the weight acting here and pushing it down. And what is pulling it up? The force that is pulling up is the surface tension. This is the surface tension, in this case air water, and acting at a certain contact angle theta. So is that surface tension gamma air water cosine theta acting all around the perimeter, which is 2 pi r, is the force that is pulling up. So now we have everything set for us. We cancel the pi's, we cancel the r, and we see that the capillary rise is equal to interfacial tension air water cosine theta over r g raw water. Notice the importance of the radius. So even though the interfacial tension air-water is a small value, the radii between soil grains can also be very small. In clays, it's in the order of micrometers, nanometers. And so this becomes very small, and the capillary rise can be quite high. Now, because the water is being pulled up, of course, the water here is actually in tension. So the water is experiencing pulling forces, is putting it into tension. Now, we can make the story a little bit more complex because our pores are not really cylinders. So imagine that we have a pore that has a necking, and so when the water reaches this point, look at what is going on. Here we have the alpha angle of the wall, and this is the contact angle. And now this equation is modified, and we are going to have theta minus alpha. And I'm going to be more precise here. This is at location X, or location Z, location X, above a certain point of reference. And this will become the radius at that point of reference. And so as we see, the shape of the pore begins to have an important effect on capillary rise. And both interfacial tension and contact angle are totally interwoven in defining this phenomenon. Next, let's explore just a simple water droplet. And if I have a simple water droplet in the space shuttle, we are at a zero gravity, and if we were able to measure the pressure here, U water, and compare with respect to U air, would there be a difference? Well, let's make a free body diagram. So this is, we just cut the lower half, and here we had the interfacial tension, gamma air water. And here we would have the pressure of the water, U water. And of course, from the top, you would have U air. And so by force equilibrium, U water minus U air times pi r squared, where r is the radius of the droplet, is going to be equal to 2 pi r, the perimeter of the droplet, times gamma air water. So the excess pressure in the water is this value, which is, we cancel the pi and the r, and this is U water minus U air is equal to 2 gamma air water, interfacial tension between air water and r. Once again, this is telling us that the smaller the pores, the larger the difference between the water and the air pressure. Now, in this case, the water is under compression. As we will soon see in our soils, the water will be typically under tension, and we will see why. So let's explore the next phase of this exercise. The story gets incrementally more interesting. So let's explore now a granular material. If I look at it from the top, let's say that it was a simple cubic packing, so this is what you would see from the top. But in order to visualize what is happening in the pores, this is the top view, I'm going to show you a cross-section that pretty much goes across the pores. So let me create this view. When we do that, we don't see the particles contacting, and so if I take this AA view, the result is as follows. I have pretty much columns of particles, one on top of each other, but once again, I'm looking at them across the main diagonal. And now, let's put water. Let's say that at the beginning, this was totally submerged. Case 1, condition 1, this was submerged. Condition 2, the water begins to evaporate and eventually reaches the surface. And at this point, really, nothing has changed. The effective stress, everything remains absolutely the same, so this is condition 2. But thereafter, the story gets more interesting. As water continues evaporating, the interface begins going down, but as it goes down, it likes to hug the particles. And so if I zoom in on one particle when the water is at this elevation, if I zoom in on one particle, this is a particle and the meniscus going like that, and this is the particle. And so if the meniscus is hanging from the particle, it is creating a force. The force that it experiences because the meniscus is hanging from it has to be equal to 2 pi r, the radius of the particle, times the interfacial tension between air and water. And that can become a significant force. But there's one more thing that is taking place here. The water is being pulled up. So all these menisci really want the water to go up. So the water is also experiencing tension. And the water is experiencing tension related to this pore radius, r pore. And as we saw before, that change the difference in pore pressure between air and water, and in this case air is greater than the water because the water is under tension, is equal to 2 interfacial tension over radius of the pore. And this came from our last expression when we were looking at the water droplet. Now, this capillary pressure creates another force, which is due to the suction that particle experiences, because it has a suction at the bottom, it doesn't have at the top. So there is another force which is equal to pi r particle square times delta U. So the total force acting on each particle is equal to F1 plus F2. So these forces can become increasingly more significant as the pore sizes become smaller, because the pore radius, remember, for a simple cubic packing, the pore radius will be equal to square root of 2 minus 1 r particle. That becomes equal to r pore, 40% of the size of the particle. So we see that all this is determined by the particle size. Finally, let's consider the case when now the water has evaporated enough that has reached this level. So the menisci, and when the water table is at position 3, the menisci may be here. And when it is there, the water may have remained at menisci. That's called the pendular regime. And when it is in the pendular regime, now the story gets more interesting, because if these are the particles and you see the menisci, and this is the water here, so we have 2 effects. On the one hand, this is the interfacial tension air-water pulling, and so if you imagine that both sides are pulling and also pulling from the other side, this is going to put the meniscus in tension. They are trying to stretch the meniscus out. On the other hand, because of the tendency of the interfacial tension to contract, if I look what happens on the equatorial plane, there is this equatorial plane wants to contract and increase the pore pressure. So now I have 2 curvatures. One is the curvature of a circle that would be tangent here if the contact angle is 0. And so we're going to call this a radius 1. And then we have the radius of the meniscus at the middle plane, which is radius 2. And what Laplace did was to demonstrate that the actual pressure in the meniscus relative to air pressure, so this is U water minus U air, is going to be equal to the interfacial tension air water, and we need to take into consideration the 2 curvatures, 1 over R1 plus 1 over R2. Notice that R1 is creating tension, R2 is creating compression, but because R1 is smaller than R2, this factor becomes larger, and now we have that the water pressure is negative. Water in the meniscus is under tension. And we can go and recompute the forces that now are exerted on the particle. And if this is the meniscus and I draw a free body diagram, I have the surface tension along this perimeter, pulling the particles together, and the suction in the water, bringing the particles together, and that gives me the total net force that is acting between neighboring particles due to capillarity, similar to what we did here. There will be two force components. The one caused by the suction is significantly larger than the other one. Notice that in Laplace's equation, the radius R1 and the radius R2 actually have different signs. So if you measure the radius from the outside, one is positive and the other one is negative, and it has to be consistent with the negative pressure that you actually conclude that takes place inside the meniscus. Now, so far we have highlighted the importance of interfacial tension, contact angle, the shape of the pore, the longitudinal shape of the pore. And so let's summarize some of these again. And imagine that I have a pore with a necking, which is effectively what happens when we have a granular medium, we have pore throats throughout, and that I am going to push, let's say that this was filled with water, and if it is filled with water and is water wet, this wants to push, advance to the left, but I'm going to push with air. And I have a higher air pressure than the water pressure because the air is working against the interfacial tension, creating a pressure which is equal to the interfacial tension air water times 2 pi r times the cosine of the contact angle. Now, as I advance, this air pressure gets higher and higher because the result is that the capillary pressure is inversely proportional to the radius. So it gets higher and higher. And so if I plot the pressure of air, U air minus U water, so there is a certain pressure, and by the time I get to the neck, it increases and then it decreases. Now, let's say that we have pushed the air all the way here, and now I'm going to let the water come back, and I measure the difference in pressure, and as you can imagine now, the water is actually driving the process, and the wettiness is driving the process, and so depending whether it is oil and water, etc., we may also have that the difference between the two fluids actually gives me a negative pressure. And so this depends on the wettability. This is when the water is wetting, and this would be when water is non-wetting in a Teflon tube. Now, if I change the interfacial tension by, for example, running this experiment in a pressure vessel where I confine CO2 or the gas, this is going to begin decreasing. It's going to have the same shape, but it's going to begin decreasing because there is a decreased mismatch in the interfacial tension between the two fluids. So this is the effect of decreasing interfacial tension in both cases. I can run another test in which I play not with the surface tension but the contact angle, and there is one more case that would emerge, and that is that it could be coming here and then it jumps and it comes back. And now that is when I change the contact angle. So the upper ones where the material was wetting, this is when the water is not wetting, and this is some intermediate condition. So what I'm trying to highlight here is that the pressure invasion curve depends not only on interfacial tension, is very sensitive to the geometry of the pore structure, but also to the wettability. In fact, wettability plays a much more critical phenomenon. Of course, there are instabilities in this process, and you may search for Haynes jumps, because once it jumps here and you keep pulling, then it doesn't want to let go, and then all of a sudden it jumps, and sometimes it may leave droplets behind. So those are called Haynes jumps. Now this is the longitudinal pore geometry. If we actually look at the pore geometry, it's full of crevices and little corners and along the surface roughness of the particles. And so what is the effect of the transverse geometry of the pore? Let's get a very weird example, but let's say that we're working with a capillary tube that is a square. So at the beginning, it's filled with water, and now I begin pressurizing U air, and while I hold the U water constant. This is a very long capillary tube. And so as you can imagine, I increase the U air, and so the U air begins to increase, but I don't push the water because the water likes the pore. In other words, if I look at it in cross-section, the water is still here. But it gets to a point that I manage to invade a sausage of air through this pore when I reach this size. And all of a sudden, when I reach this size, I had initially the water saturation was 100%, and all of a sudden increases, and this jumps at when the air enters. There is a big jump, and thereafter I have water only at the corners. But if I have a way to control the air pressure relative to the water pressure, so on the other end I have a porous stone and a higher entry value ceramic, and so I can control the water pressure and measure the air pressure. The more pressure I put in the air, the more I'm going to squeeze the water out. So as I continue increasing the air water with respect to air pressure with respect to the water pressure, this is going to increase until I pretty much dry the soil. So this is a capillary, this is capillary pressure, capillary versus water saturation. And this is going to be at the heart of the soil water characteristic curve and many other examples that we are going to see from the energy sector and the geotechnical field. So summary, the longitudinal pore geometry and the transverse pore geometry are very important in capillary phenomena. Second, we tend to put lots of emphasis on interfacial tension because it's right there in Laplace's equation. But actually, the cosine theta, the contact angle, has a very important effect as well. And whether it is there or we can manipulate it, it can create very distinct systems and the possibility of enhancing oil recovery, for example. So to conclude this video, let's explore some implications. And some of them will appear surprising, but here we go. If I have a capillary tube and I put water inside, will the water remain in the tube or not? Well, as you may remember, the tube, if the water is wetting, the upper meniscus is with the receding contact angle, while the lower meniscus is with the advancing contact angle. And because of the differences, when I add up this force around the perimeter and this one, I will actually be able to hold a meniscus which can be quite significant, hanging in there without falling because of the hysteresis in contact angle. Similarly, we can have another example. So let's assume that this is an anticline for an oil reservoir that is filled with oil. So this has the unit weight of oil, and this has the unit weight of water. And if you go back to the analysis of effective stress, you will remember that because at this interface, both oil and water have the same pressure, and because the mass density of oil is lighter than water, here, at this interface, the oil will have a higher pressure than the water. So this is U water, while this is U oil. And so this is the capillary pressure, the delta U, that the seal layer will have to hold. And because the capillary pressure is inversely proportional to the pore size, you can right away compute the pore size relative to the height of the oil pool. And this could be as well with CO2, etc., different fluids. So you can already study seal capacity of materials. The story gets more interesting as well for soils. For example, if a soil similar to what we had before, remember that we are looking across a diagonal plane, and we started with the water here, and then it begins drying. And then let's say that it invades this pore before any other pore, because this is the largest. It will invade into the largest pore, so the meniscus will be here and here. And now if I look at that instant, actually this particle is being pulled. Look at the summation of those two forces. It's being pulled in this direction, this one in this direction, and actually that pore is increasing in size. And I can continue now. That leads to preferential invasion. And if I continue this, I'm going to understand the concept of desiccation cracks. And this is the fundamental. There is no tension capacity in the soil. It's all about the preferential water invasion and the invasion of the capillary meniscus, the surface interface, the interface between air and water, and how that causes the displacements of the grains. Finally, I started talking about the lungs. And so let me come back and say something about the lungs. This is our respiratory system, and then it goes to the lungs. And when it goes into the lungs, if we zoom in here, these are the alveolus, and these are little pockets where on the outside we have the body fluids, and on the inside we have air that comes in. And so blood comes into the alveolus, releases the CO2, takes the oxygen from the air, and goes back and circulates through the arterial system. Now, every time we breathe out, we contract the alveola. So the alveola becomes smaller, and if that's the case, the capillary pressure would increase and the alveola would collapse. So remember that the capillary pressure for a spherical system will be 2 air water over the radius of the alveola. As the alveola gets smaller, the capillary pressure increases and it will collapse the alveola. And that is problematic. So what actually happens is that in our lungs we have surfactants. And you may wonder what surfactants are. And so the first thing to recognize is the meaning of the word. And surfactants means surface active agent. It's a surface active agent. It alters the interfacial tension. How does that happen? Well, imagine that I have a water droplet and I put surfactants, and so when I contract it, this is in the case of the lungs, so the water is on the outside, the air is on the inside. When I contract, the surfactants come closer together. And so 2, 4, 6, 1, 2, 3, 4, 5, 6. And now the surfactants begin to repel each other. So the surfactants, when the density increases to a critical point, they don't want the interface to shorten and decrease anymore. So if I plot, this is when I breathe in, this is when I breathe out. So if I plot the interfacial tension of air, water in the lungs, when I'm breathing in, the interfacial tension goes pretty much to 72 millinewtons per meter, and the surfactants are far away from each other. So the surface tension is here, so this is breathing in. When I breathe out, the surfactants come close together, they repel each other, and the surface tension decreases almost to 0. And so this is when you breathe out and the alveoli contract. Look at this amazing self-regulation in nature. Without pulmonary surfactants, we would die. And this self-regulation mechanism is amazing, and we also see it as fluids migrate through the porous structure of soils and the subsurface. By the way, many times babies are born lacking pulmonary surfactant, and doctors in the room know exactly what is going on, and they will spray pulmonary surfactant into the lungs, saving the baby's life. So indeed, capillary phenomena is relatively simple, but when you bring them all together, it's just fascinating.